And last, for example, you can you even evade app stores. So the one I'm using here is the Loyi DBT shell. DBT shell, I would say, is one of the very common DEX encryptors used in scam APKs. So it's quite unique that because it's that it hollows out the whole DEX. Basically, what hollow out means is that maybe you have 100% DEX files. It will maybe like 5% go into this path, 5% go into another path. Then each one go to very different paths. So when it wants to being run in during runtime, it only joins back everything, then makes it into the whole the 100% DEX bytecodes. So that is why it's very difficult to decompile for DPT shell. So that's my small sharing here. And then I believe this is the end of the whole workshop. Thank you, everyone. I will be still here. So if you guys have any issues with the labs or want to ask questions, yeah, just feel free to ask.
Hello. And the people on online here clearly. Yeah, right. All right. So we'll be continuing with the next session. Sharing, right? Team sharing screen, right? Correct presentation, right? Correct presentation, right? Okay. All right. So welcome to the second session of this workshop. So for this POH preparation workshop, I'll be guiding you guys towards cryptography, since that's my specialty. So today's agenda for cryptography will be more of a simpler approach, not as simple as ciphers, but it's the next simplest thing after cipher. So we'll just go towards it. Look at the problem, we will solve a few challenges around it. Then that should give you a gist of how cryptography should work. So So the first thing that we want to introduce, right, is actually modular arithmetic. So modular arithmetic is a part of math that is mostly the most important part of most crypto system that you will see that is being adopted in our current world modern standards, by the way. And even if you go to the post quantum side of things, modular arithmetic is still widely used and is definitely the basic foundation of things. So if you ever had any thoughts on entering cryptography, learning modular arithmetic would be a very good choice first, as that will lead you to the, I guess, is a much more simpler path for you to tackle on challenges in CTF, because this kind of thing will be very a new normal for you when you're doing more cryptography onwards. So modular arithmetic. So the most three common things that I believe you will see that uses this will be RSA, Diffie-Hellman key exchange, or also known as DHCAX, and there's elliptic curve cryptography, which is ECC. So these three are kind of like in about 20 years ago, we will consider these three as like the top three, because they are currently still one of the most widely used standards. Even currently right now, I believe most of our system still uses this, because we just don't have the infrastructure to move towards post quantum yet. But most companies and organizations are slowly moving towards it. But in the sense of CTF, we will still try to put on challenges around here, because these are the basic foundations and theories which most players should understand before they move to the more gold standard and futuristic standard, which is the quantum side of things. So modular arithmetic is basically how in Python, right? In Python, you guys should know about the percentage operator, which is the modulus operator. So the modulus operator, what it basically does, it just gives you the remainder of your value, right? You take like A mod by B, you get the remainder of this. So let's say it's like 7 divided by 3. 7 mod 3 will give you 1, because that's the remainder, correct? So it serves kind of like a clock, as you can see on this diagram here, the wraparound number system. Let's say you have a modulus of 24. Basically, right, let's say I tell you I have a number 5 under mod 24 system, then doesn't that mean 25 is just 1 under this system? 25, if you took one loop around 24, you would just be at 1 again. Correct. So that's how modulus work. And in this sense, this is how most cryptography works, actually. So let's say you have a secret message. Let's say you, for this mod 24, let's say your secret message is also 25, right? How would everyone know? How would you tell someone? How would attackers know your message is at 25? It can be 1, it could be 25, it could be 25, add another 24. You could add another 24 on it, and then it could go to like 49, add another 24 to another number, and it will keep increasing. And because all of those numbers are technically equal to each other under this mod, how would the attacker know which number are you trying to say? So in that specific, so to find out what number you mean in that specific mod is basically the inherent system which we try to use in cryptography and take advantage of. That's why RSA, Diffie-Hellman, and ECC exist, because we use these kind of systems. And that's actually one of the hardest part of cryptography to solve, because that is the reason why it is hard to solve. Therefore, attackers couldn't attack it. So moving on. So just like what I said, if we have a mod system 24, we can say 1 is equal to 25. I know in mathematics right now it doesn't make sense, because you wouldn't say 1 is equal to 25. That's mathematically incorrect. But we wouldn't say it's equal. We will put equal sign, but the equal sign looks a bit different now. You can see it's actually a triple line. So it's a triple equal signs. That means congruent. So congruent in modular arithmetic just means it's equal to each other, but only when it's under a mod system. So under a mod 24 system, 1 is congruent to 25. 25 is also congruent to 49. 1 is also congruent to 49. They are not wrong. They are correct. You are correct if you say like that. But if you say they're equal, it's a little bit mathematically incorrect. Right, so you can see on this example, we can say 17 is congruent to 2 under a mod 5 system, because when 17 mod by 5, 3 times 5 is 15. That's the maximum you can divide off, right? So 17 minus 15 is 2, the remaining is 2. So 17 technically is congruent to 2 under a mod 5 system, right? So another example would be 23 under a mod 5 system would be 8, because if you take 4 times 5 is 20, another 23 mod 5 is 8, because 23 minus 8 equals 15, yeah, and it's a multiple of 5. That is another example of it as well. So these are congruences, which is the basic foundation. Then next is basically some simple operations in modular arithmetic. Since now that you know how congruence works, there's actually not much differences. Plus minus multiply divide still works the same technically. So there's not much difference, but the only difference is on divide, the division part. So you don't have to focus on addition, subtraction, multiplication. They are all the same. The only part you have to focus on is the division part. So division part is the part where it's a little bit weird, because you technically can't divide something inside a mod, but we made it so that in other mod system, when we divide something there, we don't call it divide. We call it an inverse modulo. Basically, we are trying to find something that multiplied by that number will equal to the divisor. So you can see a divided by b mod n, we can technically say is a times b mod n in another way. We are trying to find the other number, which we will call it the inverse modular number. For this inverse modular part, it will be crucial later on RSA, where I'll show you later on if you don't understand yet. So modular inverses, let me guide you through what is modular inverses. So modular inverse technique, most of the time we use modular inverses in the sense of we are trying to find this number x, so that if you multiply a and then you mod by n, it should give you 1. So basically, you need to find a number under this mod. If you multiply some number a, it should mod and give you 1. If it doesn't give you 1, don't call it a modular inverse. It's not a modular inverse, right? So this relationship is the most important thing for RSA, and we can actually find this through using the extended Euclidean algorithm. If no one understands what's the extended Euclidean algorithm, you can go off to YouTube and you can see how they do it by hand. But of course, we are not going to do it by hand. We are just going to write it on scripts, because there are algorithms for us to already know how to do the extended Euclidean algorithm. So extended Euclidean algorithm basically tells us that ax plus ny equal the greatest common denominator of a to the n. So if the greatest common denominator is 1, then we know that x mod n definitely have a modular inverse of a. Basically, this is like a way of you to it's like a way for you to straight away find out the modular inverse just by doing that GCD. It's that simple. And there are a lot of scripts out there you can just type in and you will instantly know whether they have a modular inverse. And in Python, you definitely you don't even need to write any scripts. You can just use the power function. You just type the power by something. Let's say you have a variable a, you want to find its modular inverse under n. You can just type power a -1 and n. That's it, and you will find the modular inverse if it exists. If it doesn't exist, then it won't appear, I guess. So going next, fast modular exponentiation. So this is just extra info. So basically, this is how you can see slowly we are getting closer to how RSA forms already, because this is how computers basically efficiently compute large power modulo n. So if you think about it, let's say we have a number a, the b power is crazy large. How can you calculate it that fast? If you don't have the mod n, you kind of can see differences, Take number A and you put a very large B number, you type it in Python, you'll probably crash your whole Python because the number is too large. But then if you put that number modulus by n, somehow you get that number faster than you don't put the mod n. Which is a bit crazy because you would think, wait, I'm powering something and then divide by something to find the mod, right? Why is it more steps, but it's faster than just not doing the mod? Because we have algorithms to make it faster, and surprisingly mod just make it faster. As you can see on the work example, we technically just calculate it by in their binary steps. And when we calculate it in their binary steps, one by one, we split the power apart, then apply it like a binary in, then we slowly mod them down. So because we split the power and then mod each of the power down, so it makes the calculation so simplified because of the mod. It reduces, then only we calculate instead of just calculate. Like if we solve a power b without the mod, that is just literal power, right? So as you can see, when we apply it to RSA's key algorithm is just M, your plain text powered by E mod N, and that gives you some ciphertext. So as you all know, E for RSA usually is 65537, which is kind of large as a power, if you were to ask me. And then for the description of RSA, just takes your ciphertext powered by D mod N and become by, and it will return your plain text, right? So RSA overview. So here's the general idea of RSA. So first of all, RSA takes out two prime number P and Q, which we will compute together into a variable called n. And we shall call this n as the modulus. Please remember the name called modulus. I will call it modulus of n. Then we will select E exponent, skip the second part first, the phi n, skip that part first. We'll look at the bottom part. We'll choose an E where it's between I to phi n, and the greatest common denominator of E and phi n must be 1. Why does this relationship have to match? Remember what I taught you about modular inverses? Yes, we want to ensure that there is a modular inverse for E to phi n. Why? Because that modular inverse is your decryption key, your private key, D. If this GCD condition doesn't meet, you will never get your decryption key. It will never exist. But that in itself, surprisingly, is a challenge you can make as well, where the decryption key cannot be found as well. There's a challenge like that which I made before, but we'll not go through that. That's a bit too hard. So for the case, because you can see that we want D times E congruent to 1 under mod phi n. For this to exist, definitely following what I teach about modular inverses, E and phi n's GCD must equal to 1, right? There must exist a GCD equal to 1, or else D wouldn't exist, right? So after we found our P and our modulus, our E, our D, we have everything we need. Our public key, our private key, everything is done. RSA is therefore done. So the hardness of RSA actually comes from the generation of the P and Q. Because P and Q are prime numbers, let me ask you, let's say I tell you my modulus is 55. Can you know what is the P and Q? You can, right? It's 5 and 11. It's very simple. You can just calculate it off your head, right? It must be a prime number, so it must be 5 times 11. What if I tell you my modulus is as large as some 1000 digit number? You wouldn't be able to know what is the two prime number that multiply to form that modulus. And that is the hardness of RSA. Because you cannot calculate it, computers actually also couldn't calculate it fast enough. And surprisingly, for something around 300 digits, I think computers will take about 2 centuries just to be able to crack it, just to be able to find P and Q. RSA's hardness comes from not letting people know the P and Q, because if P and Q is exposed, your whole RSA might as well call it a day. It's gone, right? So in a sense, encryption I've talked about it. Decryption I've talked about it. It's exactly the same. The formula looks a bit wrong, so don't look at the formula. The previous formula was correct. So now I'll talk about the Euler's torsion function, which is the phi n right here that I talked about. So phi n is basically on here in this slide we write phi n is as p minus 1 times q minus 1. Phi n is basically this phi, we call it phi, but you want to call it Euler's torsion function of n, also fine, but we just call it phi or phi n, whatever you like. So phi n can be found using, because it's the Euler torsion function. What is the Euler's torsion function? Euler's torsion function basically counts the number of positive integers up to n that are relatively prime to n. Basically, we just want to find how many numbers that are relatively prime to your n. Basically, that's it. So if your number is a prime number, every number below you are all the numbers relatively prime, right? Because you can only divide by yourself and 1. That's it. So basically, that's why we just take p minus 1 times q minus 1, because we just exclude yourself and that's it. Because all the numbers are all relatively prime to you. So simple to understand, right? So let's say you see for n equal 15, we want to find the torsion for 15. We just have to take out all the number that can divide to 15, and then we just count it out. That's it. For prime number, is all number except yourself, basically. So significance in RSA. So we want to use Euler's torsion function basically to find phi n, then use phi n to basically calculate our decryption key, which is D. That's it. That's it. Nothing else. So RSA key generation example. So this is a very simple key generation example. Do not use this for modern standards because this will be easily broken. So P equal to 5, Q is equal to 11. So you multiply P and Q together, you get 55. Modulus is done. So calculate your torsion. So as I said, if you use prime numbers already, which you should, you just P minus 1 times Q minus 1. That's it. So 4 times 10, 40. Right? So choose the public exponent. Choose, basically, as long as you choose a prime number, you should be safe. Right? But typically people will use 65537. So try to follow the standards. And so if your E is 3, you can compute your GCD. You can see 3 to 40, the GCD is still 1. Definitely it will be 1 because you have a prime number as your E, it will definitely be 1. So compute a private exponent. So 3 times D is equal to 1 under mod 40. So what is D? Do your modular inverse, then you get 27. So public and private key. So public key, you get your public key 55 and 3. Your private key, your D is 27. Everything is done. So you can see encrypt. So if our message is 42, just 42 power by, we are missing the power, but just know the power is 3. So 42 power by 3 modulus by 55, you get 23. Then if you take 23 power by your decryption key is 27, mod by 55, you should get your 42 back. That's how RSA works. Plain, simple, just maths. Now, the numbers in actual situation will be way larger than this. This is just a very simplistic approach to it. So RSA security versus weaknesses, right? So for it to be secure, please try to use very large prime number. Specifically, you should be, right, by now standard, you should be around 2048 bits per prime. So combined together, it will be 4096 prime modulus. 4096 bit modulus, right? So right, yeah, sufficiently large. And this, if your n is 2048 bit, if you just divide by 2, then you know how large is the prime, which is 1024, right? So E should be 65537 because that's the standards. Large D derived from E from phi n. That's true. Unique key for each user purpose. Yes, always use a unique key. Never reuse your RSA generation too many times because later on you will see a challenge that involves if you use it too much. So common CTF challenges involve some of these key points, which is basically they give you small PQ primes and some small n, small e, small d, reuse n with different e values, a lot of ways, but these are the most easiest example I could give off, which is this. These are the, if you were to see those kind of easy RSA challenges, these are the typical configuration problems they will give it to you, which is why you should know how to counter it and get the basic knowledge of it, because most people I see right now just solve it by AI either way, so they wouldn't even understand the foundation, right? So let's look at the first challenge. So textbook RSA, you can go to the GDCTF, right? You can go to the GDCTF and then refer to the first challenge. It's exactly called as textbook RSA. Okay, try to download the file. You should only get an output of txt, right? Or is that, or did I mess up anywhere? Are you guys getting just an output of txt, or did I add too many files? GG. I hold up. Right, I have a. Why? Yeah, I can open.
I'm sure it's good for them.
Okay. Whoa, 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 whoa. Hold up. Brother. What the fuck? Holy shit. Right, this is the link. This is fine, right? So I have you guys downloaded textbook RSA's attachments? It should be just the output of txt, if I'm not wrong. If you guys get there's no output, cannot find out. Wait, chances they cannot find it. The textbook, the challenge.
Something to do with the account. Hey, can you do something else?
Well, need to click it up, but the resolution is like shit. I'm just saying. Have to do like this. What's the resolution? Let's see. Huh? What?
Where's your phone? Guys, for the crypto labs, you're supposed to access the platform and then the challenges will be on the platform. So if you don't already have the IP has already been sent on Teams. So normal.
This platform is
You know. Hey, which are you on? Are you on the app?
okay. They change it down first. Server down already. Can I just publish it on Teams? I mean, it's all static. For I'll just publish all the challenge file on Teams. Then you guys can just download it there because it's all just static attachment either way. So there's no need to follow any connections, right? Hold up. Let me just upload everything. All right, the textbook RSS challenge has been uploaded on Teams chat. Just go to the Teams chat and you can just download it. It should be a very quick challenge. Yeah. Yeah. Why? Is it down? Huh? Yeah. How?
I think
I mean, right now also. I mean, worst case, we just everything manually send into chat, but should be fine, I think. Right, so for anyone that's trying this challenge currently, let me just, I mean, from this slide you can already see. So, right, okay, hold on. All right. All right, so from if you can look at the challenge right now, the output.txt, you should see just the modulus n, the exponent e, and the ciphertext c, right? That is the case, right? For everyone, it should be that. That's the case, unless you downloaded something else. So for this challenge, I want you guys to get familiar with RSA. So this is a very simple example of a very small modulus, right? So the modulus itself is actually considered very small in this case. This is probably the smallest modulus I've ever made in my life, actually. So yeah, this is very small to the point even my plain text has to be very small as well, right? So if you can recognize a modulus is this small, around this size actually, based on the output of txt, you should just go and find some factorization tools. A very well-known factorization tool I can introduce to you guys is actually called FactorDB. Can just search it out, type it on Google, FactorDB, factordb.com if I'm not wrong. Just enter to the site, send your number into there, press factorize. If you can see two numbers come out on your screen, that means it's factorized. If it doesn't, meaning the number is too big or it hasn't been factorized before yet. Very simple. So typically of this size, if you do go to FactorDB, it should be able to factorize. I did double check, it does factorize on FactorDB. So you should be able to see your two prime number there, right? So copy your two prime numbers, put it as P and Q, and then you should be able to solve it by default. For the solving part, if you're not sure about the script, I can guide you through the script. Hold on. Right. So for your first ever RSA decryption script, please refer to here. It will look something like this. So the only package you need is PyCryptodome. I will type that in Teams right now so you don't download any wrong packages. Please do not download the cryptography package by Pip. That is a very bad package to download. Do not ever download it. If you download that, then only you download PyCryptodome, you are cooked. Your library will not work. It will not function properly. So you will have to revert and uninstall cryptography module, then only install PyCryptodome, which is a very tedious thing to do. So just go and install PyCryptodome if you don't have this package, which I assume most of you guys probably wouldn't have. PyCryptodome. If you want the full function, just type this, by the way. Oh shit. This is for Windows user. For Linux user, I think it is. Just try any of it. Because if on Windows, if you download the pip manually, it's in your environment, you should be able to just type pip install PyCryptodome, no problem. But the reason Python updates, they already included pip by default. So you don't have to install pip externally. Just put a tag m, and then you can enter pip itself into the command. And for Linux users, I think pip is by default there already. So by default, it should be in the environment. So you should be able to just type pip install PyCryptodome if I'm not wrong. But in the case that if it says it doesn't recognize pip as a command, just add a Python 3-m in the front. All right. So this should solve all your problem. If you did do this and you try to use the package and still something goes wrong, just delete every package in your library because you've definitely downloaded something else already. So this is the most standard, most clean way of doing RSA. I say clean because this is truly the cleanest I've ever written as well. So look at this. NEC is right here. If you go to FactorDB and you decrypt the N, you should be able to get P as this, Q as this. You can calculate your phi based on P minus 1 times Q minus 1 as we have discussed. Then for D, as I have said, just use the power function and put power -1 phi because it's E inverse mod phi. So inverse modulo of E under phi. Basically, that's the idea. Then if you get your D already, if you somehow didn't get any error, meaning your D exists. If you get error on this line, D doesn't exist, meaning something probably went wrong with your calculation. It's very simple for you to use error as an advantage to check whether you mess up somewhere. So this is a very good way for you to check throughout the challenges when you are in deep into a CTF challenge. If you see any error, do not just straight away send to AI. You can just use your eyes to determine that problem yourself, actually. All right. So any questions on, you can just send it on the chat or just ask. Anyone physically can ask as well, right? Because this is the textbook RSA. It's called textbook RSA because it's textbook by itself, because it's the most textbook way of decrypting it. So if you encounter any kind of CTF challenges with this kind of very small modulus, then you can just go factor DB and finish it. Just know it's called a textbook RSA because it's that textbook. All right, so does everyone manage to get the flag? The flag should be this, by the way. So try to get the flag, don't just copy it. I mean, the try to not copy it, of course. Getting it is the part of the fun of doing CTF. So everyone managed to get the flag? Probably. Right, so if everyone managed to get the flag and there's no problem, I shall move to the next challenge. Oh shit, okay. Right, so for the next challenge, let me just drop the files again. Oh. Right, so this is the second challenge, which I believe the name was something is a bit small. So for this challenge, the challenge title is something is a bit small. Yes, because that's the greatest hint I could ever give to anyone. Something is definitely very small. So for this challenge, I think there's two files. One is the challenge file and one is the output file. So let's look at it. So here's the challenge file. And the output file doesn't matter, it's always the same, it's just NEC. So here's the output challenge file. So challenge file, from a challenge file, we can see how the RSA is generated. So first of all, you can see P is generated through a 512-bit prime number. Q is generated through a 512-bit prime number. And our N is multiplied together, of course, the standard RSA creation method. So, but something ain't right. Our E exponent is only 3. Something is a little bit small, right? So our message, plain text, you can see is this. And yeah, that's about it. I just encrypt and now that's the output. Very simple, that's it. That's the whole source file. So this challenge looks a bit small, like very simplistic. If you have no, I believe some of you probably already have an idea of how to solve this challenge already, because this challenge can be solved as it is. What I mean by that is the plain text